My name is Louisa Naulia. You can call me Louisa. So today we are going to learn about probability and sample space. Image, you are a detective trying to solve a mystery. So the sample space is all your complete list of the suspects or every possible outcomes that can happen in an experiment. Meanwhile, probability is our tools to assign a likelihood score to each of those suspects. Okay, so now we are going to talk about the set. A set is a collection of objects which are the elements of the set. If S is a set and X is an element of S, we write X element S, just like this. And if X is not an element of S, we write X not element S. A set can have no elements, in which case it is called the empty set, denoted by like this. Sets can be specified in a variety of ways if set contains a finite number of elements, say x index 1, x index 2, and x index n. We write it as a list of the elements in braces, just like this. Okay, next. The example. The set of possible outcomes of a die roll is 1, 2, 3, 4, 5, and 6. And the set of possible outcomes of a coin toss is head and tails, denoted by like this, H and T. And S equal to x1, x2, and so on. And we say that S is countable infinite. Yes. Alternatively, we can consider the set of all x that have a certain property p and denote it by like this. X given x satisfies p. For the example, the set of even integers can be written as x given 0 less than x greater than 1. Note that the elements x of the latter set take a continuous range of values and cannot be written down in a list. Such a set is said to be uncountable. If every element of a set S is also an element of a set T, we say that S is a subset of T. And we can write S subset T like this or T subset S. If S subset T or T subset S, the two sets are equal, and we can write S equal T. It is also expedient to introduce a universal set, denoted by like this, which contains all objects that could conceivably be of interest in a particular context. Having specified the context in terms of a universal set, we only consider sets as that are subset of universal set. Here, set operations. The complement of a set S with respect to the universal set is the set X element to universal set given X not element to S. Of all elements of universal set that do not belong to S, and is denoted by S complement. Note that universal set complement equal to empty set. The union of two sets S and T is the set of all elements that belong to S or T or both and is denoted by S union T. And the intersections of two sets S and T is the set of all elements that belong to both S and T and is denoted by S intersection T, just like this. Okay, next. Thus, S union T equal to X given X element S or X element T, and X intersection T equal to X given X element X and X element T. In some cases, we will have to consider the union or the intersections of several, even infinitely many sets defined in the obvious way. Okay, now we have a Venn diagram. So in this picture, A is S intersection T, and B is S union T, and C is S intersection T complement, and E means T subset of S, and E, the set S, T, and U are disjoint, and F, the set S, T, and U from partitions of the set of universal sets. Okay, we have reached the end of the reason. So the main takeaway is that sample space is your complete list of all possible outcomes, and probability is the number that tells you how likely one particular thing on that list is to happen. If anything is still unclear, feel free to ask or leave a questions in the comment sections. But if this short explanation was easy to follow, don't forget to give it a like and share it with any friends who might need to learn this too. Hope this was helpful. See you in the next material.